And number 16, working more with volume, similar solids. This is section 914, and this is something that we did in unit 8, section 2, like something. It was like 8.2 point something, and we talked about ratio of area. So we did, this isn't my name, but ratio of areas. And I can only go over it briefly, okay? But there's a difference between a side ratio in similar shapes. Like, say you have two triangles, like these two guys, and these have lengths. Let's say they're 1, 2, 3, and this was 3, 6, 9. We would say that the length of this side compared, well, first of all, you say these triangles are similar. They're similar because they have the similar side ratio. If I compare this side to this side, I get a 1 to 3 ratio. If I compare this side to this side, I get a 2 to 6 ratio. I compare this side to this side, I get a 3 to 9 ratio. All these actually happen to be 1 to 3. So the fact that they're all 1 to 3 means that these are two similar shapes. Now, the side ratios were 1 to 3. But the ratio of area, I'll call it AR. Well, no, I think this is how I did it. But the ratio of areas is different. It's not 1 to 3 because the question always is, how much bigger is the triangle? Just because each side length is 3 times bigger doesn't mean the triangle is 3 times bigger. In fact, this is something we talked about or proved before, and I know this isn't drawn to scale, but I can take this triangle here, and I can fit it into this triangle 1, 2, 3, 4, 5, 6, 7, 8, 9 times. Okay, so this triangle gets dumped into here. I can fit it in 9 times. So the ratio of areas, well, actually, here going back to ratio of sides again, it says, how many times can I fit this side over here? 1, 2, 3, right? That's what ratio of side means. Ratio of area says, how many times can I fit this area into here? And that's where you get these 9 different triangles. So that's the difference between the two. So the ratio of areas is 1 to 9. Okay, this is a visual example. The thing we talked about before was that if we take the ratio of sides, compare it to the ratio of areas, no matter what it is, it always looks like you take this number and you square it. By that I mean the top and the bottom. 1 squared is 1, 3 squared is 9. Your ratio of sides, I should put RS to be consistent here. Your ratio of sides is some value. Your ratio of areas is the same as your ratio of sides squared. Take the ratio of sides, square it, you get the ratio of areas. The reason is because you're accounting for a length one way and a length the other way as well. Everything grows by X amount of times. In this case, everything grows by 3 times as much. If it's area's half base times height, you take the base and grow it by 2, or by 3. You take the height and grow it by 3. 3 times 3 is 9. That's why this goes that much bigger. Okay? So that's a brief go around into ratio of areas. Now we're talking about ratio of volumes, and honestly, it's not going to be much different. There really is only one difference, and it's that we're looking at 3 dimensions instead of 2. But before we do that, let's talk about net and prism to make sure that we understand it the other way. We've done prism to net, meaning the 3-dimensional look of this thing, to unfolding it and making a net. Let's make sure we can do it the other way as well. Okay. First of all, you see the different grids here, and you can see the bold areas where this thing essentially unfolds. We called this rectangular portion and the divisions the set of the lateral faces. So these are lateral. And the top and bottom, your bases. Now, they're not always drawn like this, and in fact, you can create it your own way. And I hope they draw it this way for you for the most part. But remember, the bases are the unique ones, the ones the the ones that define what kind of prism this is. So I look at these two bases right here, this guy and this guy, which should be congruent, by the way, and you say, well, what shape are these? And these are rectangles. So this is called a rectangular prism here. If these were triangles, like if they looked like that and that, then it would be a triangular prism. Now we've talked a lot about what, how you get the area of a net, of the surface area of a net, and it's based on taking the perimeter of your base. So keep in mind, if this was a triangular prism like that, you'd be adding up 3 sides, which means there would only be 3 sides right here, not 4 in your lateral faces. But I digress. Let's go back to what we're talking about here. How do we make this net into a prism? So let's start with the bottom base. Okay, I didn't want everything to erase. Okay, anyway, who cares? Let's start with the bottom base here. This one down here. Okay, it is a 3 by 2. In fact, here, let's start numbering these off. 2, 3, 4, 3, 2, 2, 3, 4, 2, and 2. Excuse me. And on the inside, this is a 3, 4, etc. Okay. I'll start with the bottom base, because that's kind of how this is going to be drawn. Think of this like isometric dot paper, sort of. If I want to do this like a 2 by 3, here's 2, here's 3. Okay, that's like this section right here, sort of. And then these parts fold upward, okay, and the lateral faces are the ones on the side. So this goes up 4, right there. And then you end up closing everything off after that. I should have probably used the line tool, but we're okay. Okay, and if you want to match up the grids, yeah, let's use the line tool for this. If you wanted to match up the grids, you'd say, well, this goes 3 across. Well, I could do that better. This goes 3 across. This goes 4 across. Okay, this goes 2 across right here. And everything obviously goes over the top and matches up like that as well. And this goes 4 across here. Okay, so this is the prism if I folded everything together. Now, I don't have like cubes to work with for you to say how this works, but this one folds upward, this one folds downward, these ones fold together. And they form to make this. Okay. So everything's closed off that way. So that's from net to prism. Right. Okay, so that's enough to talk about that. Now let's go ahead and take this prism and say, well, what if we grew it? Okay, what if we took it and grew this by a little bit more? Now I can probably end up doing this for you and help you out here. If I move it and duplicate it. And I'm going to give you one example of duplicating it and growing it, and after that, you'll have to be on your own with it in terms of understanding it. Let's drag over. This thing is problematic. Okay. If I took this whole thing and made it like twice as big, all right, pretend like, well, let's see. I want to make every length twice as big. Okay, so see this length right here? Now let's say it's twice as big. This is 2 times that. Okay? So what I'm going to do, because everything's twice as big, is still use the same units, whatever they were. Excuse me. And I'll draw some more things in right here. So before this length was 3, now this length is twice as big, so it's 6. So that's why I'm drawing in some more things within here. Okay, this is 6. This is 8 now instead of 4. Okay, you can count them up. Instead of 2 here, this is 4. Wait, did I say instead of 8, this is 4? I meant to say instead of 4, it's 8. If I said instead of 8, it's 4. And that's a bad drawing, but 6 across. Okay, so now we can look at these 2 different shapes. This is now 4, 6, and 8. high. Okay. So what we're doing here is we take linear scale ratio. If I take the original dimensions, the length is 3, the width is 2, the height is 4, the volume is the area of the base, which is 3 times 2, which is 6, times the height, 4, which is 24. So looking at the original volume the entire way down, all of these will be 24 of the original volume. And new volume will be based on my linear scale ratio. So when that says 2, what that means is we're looking at a 2-to-1 scale ratio of... probably too far back, but we're looking at a linear scale ratio of this to this. I took every length and grew it by 2. It goes 2 to 4, it goes 3 to 6, a little better, goes 3 to 6, and it goes 4 to 8, right there. So everything is twice as big. Okay, the question is going to end up being, though, what is my ratio of volumes? What that means is how many of these can I fit into here? Okay, there's a difference between fitting a number of sides into each portion and fitting this prism into this prism, because it's 3 dimensions. Okay, and I'm going to find the best way to make you visualize it and see it, but you're going to have to go with me. Okay, let's bring it back. If this is a 2-to-1 ratio, that means every length grew by 2, and we saw that before. This is 6, this is 4, and this is 8. Okay, everything's twice as big. Now, the original volume was 24. The new volume, I want you to keep in mind, the new volume is not twice as much, and you can't just assume that it is. And we're going to see what it is in a second in comparison to this. But the new volume is area of base (6 times 4) times the height, which is 8. Okay? So your new volume is 24 times 8, and I'm going to have to whip out the calculator in a second for later ones, but 24 times 8 is, I already need the calculator, 20 times 8, 192. By the way, these are cubic units. Ratio of volume, so now we're going to see, okay, the ratio of sides is 2-to-1. This is your RS, which means every side grew by twice as much. Ratio of volumes is saying how much bigger is 192 in comparison to the original volume, 24. So while the sides were 8 over 4 is 2 over 1, etc., we're going to see what 192 over 24 is. Take out your calculator if you need to, but you're going to get that it's 8 over 1. You get the number 8, but as far as a ratio, it's 8-to-1. Okay? Now I'm going to try once with you to see if this makes sense. If I can't do it by then, you're going to have to keep rewinding and see if you can make as much sense of it as possible. See if I can change the color of this. That would be awesome. Awesome. Okay. 8-to-1. What that means, remember the triangle example. The sides fit only 3 times as much, but I could fit 9 triangles into there. So see if you can imagine how I fit 8 of these into here. Now, perspective has to come in mind here. See if this intersection makes sense. We place it in here. 1, 2, 3, 4. Now moving to the back. 5. Somewhere back here. 6, 7, 8. Okay. Now, because this thing acts as a solid, even though I can transparently go through it, you can't see the back corners. But again, notice where I'm fitting these. Like even right here, these are 2 different places. If I go, oh gosh, if I go 1, 2, okay, you notice the difference between 1 and 2, etc. I can go 3 and 4 up there, and now you go to the back, 5, 6, 7, 8. So I fit 8 of those into there, even though each side only grew by 2. Okay, that's because when we're looking at volume, we're referring to 3-dimensional space, and we're looking at every direction which it grows by 2. Or better yet, 2 times 2 times 2, which is 8. Okay, that's the only visual one I'll be able to do for you. The rest we're going to have to play with and keep in mind. Ratio of sides right here will be 3-to-1. If the linear scale ratio is 3, I'm multiplying every side by 3. So 3 times 3 is 9. 2 times 3 is 6. 4 times 3 is 12. So the new volume for this one is area of base, which is 9 times 6, times your height, which is 12. 54 times 12. Going to whip out the calculator for this one, or the computer calculator. We get 648. By the way, I'm just going to write cubic units so you get a good familiarity with what's a right. That's a U. Okay, 648 over 24. I'm just going to make sure I got the right volume to start with because I know what I'm supposed to get based on my understanding of ratio volumes. You get 27 over 1. Okay, I'm going to skip 4 for now, and then we'll go back and confirm it. I'm actually going to go to R here. Let's zoom out a little bit again so we can kind of see everything. Okay, R, if you get a linear scale ratio of R, people might ask, oh gosh, what does R mean? Okay, later when you go into more algebra, stuff like that, you're going to be referring to things arbitrarily. Arbitrarily. In other words, we're not looking at specific numbers, we're looking at the generalization of it. Okay, if your linear scale ratio is 1, we grow it by R amounts, meaning we take everything and multiply it by R. So if the original length was 3, the new length is 3R. And again, people are asking, well, what the heck is R? We don't know what R is. Well, that's the point. You don't know what R is. It can be whatever it needs to be. This helps you give a general understanding of what the ratio ends up being. If your similarity ratio is now R to 1, meaning for every 1 you have here, you have R here. So here, if your length was 3, your new length is 3R. Instead of 2, you have 2R. Instead of 4, you have 4R. So again, the original volume is 24. The new volume is taking the area of the base, 3R times 2R, multiplying it by the height, 4R. I have to sneeze. Excuse me. Okay, 3R times 2R. Remember, a lot of people are going to say 6R. Remember, it's 6R squared, R times R. 6R squared times 4R is 24R cubed. So this is your new volume. Okay. What's the ratio of your new volume to your old volume? Well, 24R cubed over 24. 24 over 24 is 1. R cubed over nothing is R cubed. So you have R cubed over 1. Okay, so remember, these are your ratios of volumes. It means this is how many cubes you can fit in, or this is how many prisms you can fit into your original prism. If I have one of them, then I can fit R cubed amounts into my new one for my small one. Okay, so I want you to get this relationship in mind right now. If the linear scale ratio for similar solids is R, meaning if I grow every side by R amounts, now remember, the big part is these have to be similar, okay? Because everything has to grow by the same amount. These all grew by 2. If they don't all grow by 2, then they're not similar solids, and then you can't make a general conjecture about it, or a conclusion. If the linear scale ratio for similar solids is R, meaning if my scale ratio is R to 1, it could be 2 to 1, 3 to 1, 4 to 1, etc., then the ratio of volumes is R cubed. What that means is, if my linear scale ratio is 2 to 1, then my ratio of volumes is 2 cubed to 1. 2 cubed is 8. That's where we got 8 to 1 earlier. If you go back up, this was 2 to 1, linear scale ratio. Ratio of volumes is 8 to 1. Because I grew every side by 2, I can now fit 8 of these into here. If I was able to, and if I did grow everything by 3, then I could fit 27 of those prisms into, 27 of the small prisms into the larger prism, the one that's 3 times as big everywhere. Remember, the prism isn't 3 times as big. The prism is 27 times bigger. Everything grew by 3. Okay, so that's what makes it 27 times bigger. 3 times 3 times 3, which is 3 cubed, which is 27 over 1. Okay, so imagine if your ratio of sides here is 4 to 1, your ratio of volumes over here will be 4 cubed over 1. 4 cubed is 64. So we're going to end up getting 64 over 1. Let's confirm that and make sure. Okay, and then we'll be done. Your original length is 3. Everything's 4 times as big. You get 12. 2, you get 8. 4, you get 16. Original volume 24. New volume is area of base times height. 12 times 8 is 96. Let's calculate this. 96 times 16 is 1,536 cubic units. Okay. You can use your calculator. Don't take my word for it. 1,536 over 24. I am going to calculate it to double check. I should get 64, and I do. 1,536 over 24 is 64 over 1. This is your ratio of volumes. All right. Save ourselves time. We don't have to do all this. If you know there's similar solids, everything's 4 times as big. Your volume of your smaller one to your bigger one is 1 to 64. Bigger to smaller, 64 to 1. And again, there's no real way that I can actually fit it on the screen. But say I took this right here and grew everything by 2 more, which means I'd have 8, 12, and 16. Let's zoom out to get a good example of that, though. Zoom way out. If I grew this, whoa. If I grew this, oh, I can't. There we go. If I grew this big, okay, it's hard to imagine maybe, but 64 of these little guys, 1, 2, 3, come on, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, etc. Then you move over. Boom. 17, 18, 19, 20, etc. 33, 34, 35, 40, 49, 50, 51, 52, etc. It keeps going. You can fit 64 of these into here because every side is 1, 2, 3, 4 to 1. 1, 2, 3, 4 to 1. 1, 2, 3, 4 to 1. We grew everything 4 times as big, but 64 of these can fit into here. Okay? It's the cubed amount of whatever your linear ratio is. This is 4 to 1. Really, I should say 4 cubed to 1 cubed for these things, by the way. I'm gonna zoom in one more time here. Because if your ratio, let's say, because I want to give you one more example. If your ratio is a fraction, so I'm saying 1 cubed here. 1 cubed. Which 1 cubed is 1, so it works. But let's say your ratio is 3 to 2 of your side ratio. Like if I have this guy right here, whatever, and these are all 2 or something, and then I have this one right here. Apparently I can't draw cubes, but these are all 3, and your side ratio is 3 to 2. Okay, your ratio of volumes is 27 to 8. I cubed 2. It's 3 cubed over 2 cubed. Which means you can fit whatever 27 over 8 is. Let's see, it's 3.75. Or 3 3/4. Okay, I can fit 3 1/4 of these into here. Okay, it's not really drawn to scale, but that's the idea of it. I can fit 3 1/4 of those into there. Okay. So that's what all this means when we're talking about ratio of volumes of similar solids. But yeah, it's that general idea, and I can't fit them into there for you, but I tried to trace as well as possible to get you to understand it there. And I hope it really did make sense as we did this and went along with it. So when you have questions and it says, are these things similar based on what the information you have, make sure that your ratio of sides and your ratio of volumes are not the same. Ratio of volumes should be ratio of sides cubed. So let's write that last thing, even though it's right there. Ratio of sides cubed equals ratio of volumes. And remember, ratio of sides squared is ratio of area. By the way, ratio of sides equals ratio of perimeter. Okay, signing off.